we followed on data about a meteor that landed about 50 miles away from the coast of Papua New Guinea.
A remote stretch of the Pacific Ocean has become the center of an extraordinary scientific drama, after researchers announced they had recovered tiny metallic fragments that may have originated outside our solar system. The discovery, led by Harvard astrophysicist Avi Loeb, has fueled headlines. You've probably come across rumors about how Harvard issued an emergency briefing after a discovery on the Pacific Ocean floor. Today, we'll unveil the whole truth. Let's get started. The 2014 interstellar meteor. On January 8, 2014, a brilliant fireball blazed across the night sky above the Pacific Ocean, northwest of Manus Island in Papua New Guinea. The event was recorded by US Department of Defense sensors that monitor the atmosphere for high-energy flashes, the same global system originally developed to detect nuclear detonations. Analysis of the data revealed that the object responsible, catalogued as CNEOS 2014-0108, and later nicknamed the Interstellar Meteor 1, or IM1, was moving at an extraordinary speed. Its estimated velocity of about 45 kilometers per second relative to Earth and more than 60 kilometers per second with respect to the Sun immediately distinguished it from the countless meteors that regularly enter the atmosphere. Most meteoroids arrive traveling at speeds well below this range, bound to the Sun's gravity. IM1's trajectory indicated a hyperbolic path, suggesting that it was not gravitationally tied to our solar system at all. For years, the significance of the event remained largely hidden. In 2019, Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University, and his then-student Amir Siraj examined the publicly available bolide database maintained by NASA's Center for Near-Earth Object Studies. They found that the recorded speed exceeded the Sun's local escape velocity, implying that the object had arrived from interstellar space. Loeb and Siraj prepared a paper arguing that the meteor was the first interstellar object ever detected in the solar system, predating the 2017 discovery of 1E, Oumuamua, by nearly 4 years. Because key portions of the government data remained classified, the paper lingered without peer-reviewed confirmation. The decisive acknowledgement arrived on April 6, 2022, when the United States Space Command issued an unclassified memorandum, signed by Lieutenant General John E. Shaw and addressed to NASA's Planetary Defense Coordination Office. The memo stated with 99.999% confidence that the object's velocity is sufficiently high to indicate an interstellar trajectory. This confirmation made IM1 the first officially recognized interstellar meteor on record. The meteor's entry into Earth's atmosphere released energy equivalent to roughly 110 metric tons of TNT. It broke apart in the upper atmosphere at an altitude of about 18 kilometers, scattering debris across an estimated ocean area of roughly 10 square kilometers. Because it exploded above a remote region of the Pacific north of Papua New Guinea, there were no eyewitness accounts from populated areas and no immediate recovery efforts. Loeb wanted to take a step further. Loeb's expedition and recovery. In June 2023, a multidisciplinary team led by Avi Loeb, under the umbrella of the Galileo project, set out to study the impact site of the meteor CNEOS 2014-0-1-0-8, commonly called the 2014 Interstellar Meteor, or IM1. US Loeb's expedition aimed to determine whether tiny fragments of that object still rested on the seafloor, and, if so, to bring them back to the surface for laboratory study. The search zone lay north of Manus Island, the largest of Papua New Guinea's Admiralty Islands, roughly 85 kilometers off the northern coast. Based on military satellite data and subsequent trajectory calculations, Loeb and collaborators narrowed the predicted debris field to a stretch of ocean centered near 1 degrees south latitude and 147 degrees east longitude. Depth surveys put the seafloor there at about 1.7 kilometers below the surface, a challenging but manageable depth for modern recovery operations. After extensive planning and negotiation of permits with Papua New Guinea's National Fisheries Authority and Maritime Safety Authority, Loeb's group secured the research vessel Silver Star from EYOS Expeditions. The Silver Star departed from the port of Lorengau on Manus Island in mid-June 2023, carrying a 26-person crew that included ocean engineers, navigators, research divers, and scientists from Harvard University, the University of California at Berkeley, and other institutions. Central to the mission was a custom-built magnetic sled designed to be towed across the seafloor. The sled, about 2 meters long and equipped with neodymium magnets, was fitted with cameras, suction devices, and collection trays to capture small metallic particles. Over the course of 2 weeks, the team completed a grid of sweeps covering roughly 175 kilometers of track line, dragging the sled at an altitude of only a few centimeters above the seabed, while carefully monitoring position with GPS and inertial navigation systems. Each retrieval of the sled brought up a slurry of sediment and small particles that was meticulously sieved, washed and examined on deck. By the end of the expedition, the team had recovered approximately 850 tiny metallic spherules ranging in diameter from about 0.1 millimeters to 1.3 millimeters. Most were barely visible to the naked eye. They glinted like specks of black sand. Loeb's group documented the coordinates of each collection run, photographed the particles under microscopes aboard ship, and stored them in sterile containers for subsequent laboratory analysis. The total mass of the recovered material was measured in grams, yet it represented the first tangible sample potentially originating from a confirmed interstellar object. Initial analyses began immediately after the expedition concluded. At Harvard University, Loeb and his collaborators employed scanning electron microscopy and X-ray fluorescence to determine the chemical composition of the spherules. Additional testing at the University of California at Berkeley and at Bruker Corporation facilities involved electron microprobe measurements and mass spectrometry. These studies revealed that the majority of the particles consisted largely of iron, with varying amounts of magnesium, titanium, and nickel, consistent with metal droplets formed during a high-temperature atmospheric entry. Roughly 10% of the spherules, however, displayed an elemental pattern that was strikingly different from known terrestrial or meteoritic samples. These particular grains were enriched in beryllium, lanthanum, and uranium, a combination Loeb's team dubbed Bella U type. The presence of lanthanum and uranium in significant ratios is unusual for natural micrometeorites or oceanic sediments, and became a focal point for ongoing investigation. The physical characteristics of the recovered material reinforced the idea that IM-1 was exceptionally robust. US military data from 2014 showed that the meteor disintegrated at an altitude of roughly 18 kilometers after experiencing dynamic pressures estimated at more than 200 megapascals. Modeling of the deceleration implied that the parent body had a material strength exceeding that of typical stony chondrites, and perhaps even stronger than standard iron meteorites. Such resilience would explain how fragments survived the fiery entry to form the spherules later recovered on the seabed. Scientists have advanced two main hypotheses to explain the origin of these unusual particles. The conservative view is that IM-1 represented an exotic but natural interstellar rock or metal alloy, perhaps a fragment of a differentiated exoplanet or the ejecta of a supernova, whose composition happens to differ from the catalogue of meteorites known on Earth. Stellar nucleosynthesis models allow for a variety of metal ratios, depending on the history of the parent star system, so an unfamiliar blend of beryllium, lanthanum, and uranium is not necessarily beyond nature's capacity. But Loeb has a completely different opinion on the matter. He believes that the object might have been technological debris, an ancient fragment of material manufactured by another civilization and expelled from its home system. To distinguish between these possibilities, the Galileo project arranged for isotopic studies designed to identify the stellar provenance of the particles. Ratios of isotopes, such as uranium-235 to uranium-238 or variations in iron and oxygen isotopes, can reveal whether the material formed in a different part of the galaxy. These analyses require highly sensitive instruments and careful elimination of terrestrial contamination. For now, we can only wait. Recognizing the limitations of surface-towed equipment, Loeb's team announced plans for a follow-up expedition. The next mission intends to deploy the remotely operated vehicle Hercules, operated by the Ocean Exploration Trust and capable of descending to depths greater than 3 kilometers. Unlike the magnetic sled, Hercules can hover precisely over the seabed, map it in 3 dimensions, and manipulate objects with robotic arms. The goal is to locate larger fragments of IM-1's parent body, pieces that could yield more definitive mineralogical and isotopic data. While the June 2023 expedition captured public imagination, many planetary scientists urge caution in interpreting the findings. Microscopic metallic spherules are common in marine sediments and can arise from multiple terrestrial sources, including volcanic eruptions, industrial emissions, and the ablation of ordinary meteoroids that melt upon atmospheric entry. Critics such as planetary scientist Peter Jeniskens and others have noted that without unambiguous isotopic evidence, it is premature to attribute the recovered particles to an interstellar object. The unusual Belayu composition, they argue, might reflect contamination from seabed hydrothermal processes or unidentified industrial fallout rather than an alien star system. The setting of the expedition reflects the international dimension of such research. The search zone lies within Papua New Guinea's exclusive economic zone, and Loeb's team obtained official permits and collaborated with local authorities to ensure that environmental and maritime regulations were followed. The Silver Star operated out of the port of Lorengau, bringing employment opportunities and logistical coordination with local agencies. These arrangements highlighted how scientific exploration of the deep ocean, especially when linked to potential extraterrestrial discoveries, requires careful diplomacy and transparency. Beyond the specific question of IM-1's origin, the expedition has broader scientific significance. If the recovered spherules are confirmed to be interstellar, they would represent the first direct physical samples from another stellar system ever retrieved by humans. Unlike 1I, Oumuamua in 2017 or 2I Borisov in 2019, which were studied only by remote telescopic observation, IM-1 offers material that can be held, measured, and tested in laboratories on Earth. Even if the particles ultimately prove to be of terrestrial origin, the methodology pioneered by Loeb's group demonstrates a new way to search for and recover extraterrestrial material from the ocean floor. Statistically, the detection of IM-1 suggests that Earth is struck by half-meter scale interstellar meteors roughly once per decade, far more frequently than earlier models predicted. This realization has implications for planetary defense and for understanding the exchange of matter between star systems. It also strengthens the case for additional monitoring networks capable of rapidly pinpointing impact sites and enabling timely recovery missions before ocean currents disperse the evidence. Whether these grains ultimately prove to be relics of a distant star system or simply unusual products of our own planet's geology and industry, their discovery marks a significant step in the young field of interstellar archaeology and illustrates humanity's growing ability to reach beyond the solar system. Other confirmed interstellar visitors. The discovery of objects originating from outside the solar system has transformed planetary science and our understanding of how common interstellar debris may be. The first of these confirmed interstellar visitors was 1I Oumuamua, detected on October 19, 2017, by the Pan-STARRS 1 telescope on Haleakala, Maui, Hawaii. Astronomers quickly recognized that its hyperbolic trajectory, an eccentricity of about 1.2, meant it was not gravitationally bound to the Sun. Estimates of its size ranged from roughly 100 to 400 meters, with an unusual aspect ratio suggesting a highly elongated shape, possibly cigar-like, or a thin pancake. Unlike typical comets, Oumuamua showed no visible coma or dust tail, yet its motion displayed slight but measurable non-gravitational acceleration, on the order of a few millimeters per second squared. Proposed natural explanations include outgassing of molecular hydrogen, a fragment of nitrogen ice from a Pluto-like world, or a fractal dust aggregate. Avi Loeb advanced the provocative idea that Oumuamua might not be a purely natural body at all, but instead a relic of intelligent engineering, perhaps a thin, broad light sail designed to travel between stars by harnessing the pressure of starlight. He based this hypothesis on several puzzling measurements. The object's highly elongated or possibly pancake-like shape inferred from its fluctuating brightness, the absence of a visible dust or gas tail, despite a small but statistically significant non-gravitational acceleration as it receded from the Sun, and its reflectivity, which some analyses suggested could be higher than that of typical asteroids or comets. Loeb argued that a sheet-like structure, only a fraction of a millimeter thick, constructed of strong yet lightweight material, could account for these properties while requiring no propellant of its own. He presented the case in peer-reviewed papers and in his 2021 book, Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, contending that open scientific inquiry should include, even if ultimately dismiss, technological possibilities. 2 years later, on August 30, 2019, Ukrainian amateur astronomer Gennady Borisov discovered the second confirmed interstellar object, 2E Borisov, using a 0.65-meter telescope he built himself. Follow-up observations by professional observatories showed a hyperbolic orbit with an eccentricity of about 3.3 and an inbound speed of roughly 32 kilometers per second relative to the Sun. Unlike Oumuamua, Borisov exhibited a textbook cometary appearance, a bright coma and a tail of dust and gas, making it visually similar to ordinary solar system comets. Spectroscopy revealed water, carbon monoxide, and other typical cometary volatiles, suggesting that planetary systems beyond our own produce icy bodies with compositions broadly comparable to those in our Kuiper Belt and Oort cloud. Astronomers measured its nucleus at perhaps 0.4 to 1 kilometer across. Borisov's clear cometary signature provided strong evidence that interstellar comets are not rare curiosities, but part of a broader population. The third recognized interstellar visitor, designated 3IATLAS, was found by the Asteroid Terrestrial Impact Last Alert System Survey based in Hawaii. Preliminary orbital solutions confirmed a hyperbolic path with an eccentricity comfortably greater than 1 and an inbound velocity of about 25 to 30 kilometers per second relative to the Sun. Observers soon described a long-period cometary appearance, again marked by a diffuse coma and developing tail. Although less extensively studied than Borisov at the time of discovery, 3IATLAS reinforced the emerging picture that interstellar comets are common enough to be detected routinely by modern sky surveys. Its detection highlighted the growing role of automated wide-field programs in spotting transient objects before they recede into interstellar space. These three well-documented flybys form a striking contrast with the interstellar meteor known as CNEOS 2014-0108, or IM1, which entered Earth's atmosphere nearly 4 years before Oumuamua was spotted. US Department of Defense sensors recorded IM1 as a fireball over the Pacific Ocean near Papua New Guinea on January 8, 2014. Subsequent analysis placed its velocity at roughly 45 kilometers per second relative to Earth, faster than the solar system's escape speed. This was the first known interstellar object to strike our planet. These four objects, Oumuamua, 2I Borisov, 3I Atlas, and IM1, outline a rapid shift in our understanding of the interstellar environment. Before 2017, No confirmed interstellar objects had been documented in the solar system. In less than a decade, astronomers have recorded 3 clear flybys and 1 impact. The Vera C. Rubin Observatory, expected to begin full operations in the mid-2020s in Chile, will conduct the Legacy Survey of Space and Time, or LSST, and is projected to discover many more interstellar objects each year thanks to its 8.4-meter mirror and 3.2 gigapixel camera capable of imaging the entire visible sky every few nights. Space-based missions, such as the European Space Agency's Comet Interceptor, are being planned to rendezvous with an as-yet unknown interstellar comet. These efforts highlight a growing consensus that interstellar objects are far more common than once assumed, and that sampling them can yield unique clues about the chemistry and dynamics of distant planetary systems. Avi Loeb, for his part, has repeatedly argued that the discovery of interstellar objects is more than a cataloguing exercise, drawing on the so-called zoo hypothesis, a concept first articulated by MIT radio astronomer John A. Ball in 1973. Loeb notes that advanced extraterrestrial civilizations might deliberately avoid overt contact while still observing emerging societies such as ours, much as humans watch animals in a nature reserve without disturbing them. He points out that a technologically sophisticated culture could send autonomous probes or monitoring devices on long, slow trajectories through the galaxy, allowing them to drift silently into planetary systems for reconnaissance. In his view, the high frequency of interstellar debris implied by recent detections, Oumuamua in 2017, 2E Borisov in 2019, 3I Atlas in 2025, and the earlier impact of the interstellar meteor IM-1 in 2014, means our solar system may already host artifacts of such watchers. Loeb regards the unusual behavior of Oumuamua in particular as a tantalizing case. Its small but consistent non-gravitational acceleration without a detectable cometary tail, combined with its fleeting visit and peculiar shape, convinced him that an artificial explanation deserves as much attention as exotic natural models. He has argued that dismissing the technological possibility outright would amount to a failure of scientific curiosity. His Galileo project, launched at Harvard in 2021, aims to bring rigorous, open data investigation to this frontier, deploying advanced telescopes and sensor arrays to detect and analyze unidentified aerial phenomena, as well as future interstellar objects. He envisions a scientific program that treats interstellar visitors as possible probes, subjects their remnants to laboratory scrutiny, and builds the infrastructure to catch the next one in real time. Whether these objects turn out to be natural or engineered, Loeb believes the search itself affirms humanity's readiness to step beyond its own cosmic enclosure and discover who, if anyone, is watching from the dark. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.